Hello friends, our today's topic is DUIS, means differentiation under integral sign. Let I be the integral from a to b of function x and say alpha dx, where x is a variable and alpha is parameter. Then if we differentiate with respect to alpha, then this d alpha of the integral, this integral is with respect to x and derivative is with respect to alpha, so they will not get cancelled. DUIS rule says that this differentiation under integration, this derivative is going inside as a partial derivative of the function x and alpha. What is meant by partial derivative? As we are differentiating with respect to alpha, all other variables to be treated as constant. So here for this derivative purpose x is constant. So this is the rule. In that way the integration can be obtained. We'll see some examples over this. Prove that integration from 0 to 1 x raised to alpha minus 1 upon log x dx is equal to log of alpha plus 1, where alpha is greater than 0. Now how to solve this integral? Using DUIS we will see the form. So here other than x we have alpha as a parameter, so let alpha be a parameter. It means take given integral as integration of alpha, that is x raised to alpha minus 1 upon log x dx equation 1. Now we have differentiating both sides with respect to alpha. So LHS is di upon d alpha, and as DUIS says this integration is with respect to x and differentiation with respect to alpha, that differentiation goes inside, that is under integral sign for x raised to alpha minus 1. That's why here the term of x, pure term of x, which is log x, is constant, that's why taken outside. Now treat alpha as a variable and differentiate this bracket with respect to alpha. It gives us integral 0 to 1 upon log x as it is. Derivative of x raised to alpha is x raised to alpha into log x dx. This is something d dx of constant raised to variable. Here x is constant for alpha and alpha is variable. So we know derivative of 2 raised to x is 2 raised to x as it is, and log of base, that is log of 2. Similarly here x raised to alpha's derivative is x raised to alpha into log of x. Now we have only remained quantity as integral 0 to 1 x raised to alpha dx. Now this integral is very easy with respect to x, therefore integral can be taken here as x raised to alpha plus 1 upon alpha 1 plus 1. See here, now alpha is again a constant. That is the beauty of parameter. Sometimes it is variable, sometimes it is constant with the limits 0 and 1. So we have 1 upon alpha plus 1. We are putting x as 1 upper limit minus x as 0 lower limit, which is 0. So 1 upon alpha plus 1. So this is the value of di upon d alpha. Our intention is to get this I. So obviously integrating with respect to, now this derivative is with respect to alpha. So we need to integrate with respect to alpha to get I of alpha again. So it is integration of 1 upon alpha plus 1 d alpha, which is log of alpha plus 1, because denominator's derivative is at numerator, which is 1, plus c. So see, this first integral was a definite integral and this integral is now indefinite integrals, that is limits are not given, that's why this integral constant is there. Therefore we have I of alpha value as log of alpha plus 1 plus c. Now to find this c, integral constant, to find c, put alpha. Now we have to put some alpha value, appropriate value of alpha, for which I of alpha is obtained and log of alpha plus 1 is easily obtained. So if we see, if we put alpha as 0, then we get I of 0 is equal to log of 1. We are putting here in this equation, plus c. Now what is I of 0? Come back to equation 1. This was equation 1. So I of alpha is this integral. When alpha is 0, x raised to 0 is 1, then 1 minus 1 is 0, and this integral value, that I value, capital I value, is 0. That's why this is 0 equal to, now log 1, log 1 is also 0. That's why c is also 0. Putting this value for this c, we have finally value of I of alpha as log of alpha plus 1, and that we wanted to show, that integral value is log of alpha plus 1. We have another example on DUIS. Prove that integral from 0 to infinity e raised to minus ax sine mx upon x dx is equal to tan inverse of m upon a. This is the example. Now here, other than x, there are two constants available, which is m and n. So it is up to us for which parameter to be solved. So here we'll consider m as a parameter. Let m be a parameter. So once parameter is selected, we have all other parameters as constant. So here a will work as a constant throughout the example. So as m is the parameter, let given integral be the integral of m, I 0 to infinity e raised to minus ax sine mx upon x dx. With respect to m, we get di upon dm is equal to 0 to infinity. The derivative goes under the integral cell as partial derivative with respect to m for sine mx only, because this is the only term of m, whereas e raised to minus ax upon x is constant dx. So this is nothing but 0 to infinity. Sine mx derivative is a cos mx into derivative of mx with respect to m is x, and another e raised to minus ax upon x is available. So here x is getting cancelled and we get di upon dm as 0 to infinity e raised to minus ax cos mx and dx. We know this can be solved using ready formula, as we know that integral e raised to ax cos bx dx, we have ready formula for this, e raised to ax upon a square plus b square, a cos bx plus b sin bx. And if this limit is, if this integral is definite integral, we have limits to the entire quantity here. Let's use this formula here. Here value of a is minus a and value for this b is nothing but m. So fill this formula. It is e raised to minus ax upon minus a square, which is plus a square, and b square would be m square. Then we have minus a cos mx plus b, that is m sin mx. This is our definite integral. So to the whole quantity we have limits 0 to infinity. We have e raised to minus infinity is 0. That's why upper limit value is 0. Minus lower limit, we are putting now x as 0. So e raised to 0 is 1 upon a square plus m square. Now cos 0 is 1, that's why minus a, and sin 0 is 0, that's why plus 0. And this minus is plus, that's why we have a upon a square plus m square, the value of di upon dm. Our intention is to get this I free. Therefore, integrating with respect to m, because this derivative is with respect to m, so we need to integrate with respect to m. So after integration we get I of m is equal to, this is integral of a upon a square plus m square. See friends, this a is now constant, so this is constant upon constant square plus variable square, something like this, integral of a upon x square plus a square, where x is nothing but m. We know this integral is nothing but tan inverse of x variable upon constant. Apply this formula here. This integral is tan inverse of variable is m here, so m upon a and plus integral constant c, as this is indefinite integral. Now to find c, we put something for m, the parameter which we have solved for. Now put appropriate value of m so that I of m is easily obtained, and this tan inverse is also easily obtained to get this c. Now I of m is here given integral. This was our I of f, call equation 1. Now for this I of f, if we put m as a 0, then we get sin m as sin 0 is 0, therefore entire integral value is 0. Therefore if you put m equal to 0 here, I of f is 0, therefore tan inverse of 0 plus c, and that's why c is also 0. Put this value here, we get final answer as I of m, or only integral, is tan inverse of m upon a, and that's it. So dear friends, we learned here how to solve integral using DUIS concept. When it is not easily solvable, you can use DUIS concept to solve them easily. So let's have revision to the important steps. First, we have to fix the parameter and call that given integral as I of that parameter. Then differentiate with respect to parameter, we get all the integrands solved. Then integral is solved with respect to x, whereas that parameter is constant. Then after integration is solved, we get di upon dm value. Okay, this derivative is with respect to m, that's why after integrating with respect to m, we get the corresponding value. Thank you.